Okay, this is lecture 13. We have spent already 20 minutes to have a Q&A session in Korean. So now let's go to the main lecture content of lecture 13. This is the last lecture before our midterm examination. Okay, so this was the simplified form of a drain current. So, you know, it looks already quite complicated, but compared with the Pausa double integral, it is really much simplified. Now here we have two bounds, so bounds of our integration, and this is surface potential evaluated at drain and evaluated at source. How can you calculate it? Since we are using the gradual channel approximation, we can just solve one-dimensional MOS equation twice, at source, at drain. So what is the difference between these two equations? So in this case, please use your electron quasi-Fermi potential equal to source voltage, and in this case, please use your drain voltage as the electron quasi-Fermi potential. So you can just calculate this quantity twice, then yes, everything can be calculated. So this is much more simplified. However, people even try to avoid the solution procedure to calculate surface potential. They wanted to directly use this drain and source voltages only. They wanted to avoid solution of a non-linear equation as much as possible. So that's the reason why we will, from now on, we will study some regional approximations. So this is not only existing regional approximations, but this is for inversion, and we will consider three different approximations. The first one is inversion case, but before saturation. So simply speaking, what is it? So when you come back to our previous lecture material 12, so as you can see, the thing we are currently talking about is the channel is just located in this region. Okay, so we have sufficiently good approximation between the dV over d phi s is quite close to 1. Yes, we have a sufficient number of electrons underneath the gate oxide. So when we apply certain quasi-Fermi potential, our surface potential will follow a similar amount. So that is our assumption. In this case, so we can roughly say this way. So please note that this is just this is valid only in a rough sense. So let's assume that V equal to 0. So we have just equilibrium case, drain equal to 0. In this case, actually, it is just saying that surface potential equal to 2 times phi b. So is it good enough or not? We have already seen that this is the condition for onset of inversion, and after that we will see a slight marginal increase of surface potential. It is not exactly fixed, but it is still increasing. Point is, although we apply, for example, additional 1 volt, but amount of increase in our surface potential is much lower than, for example, 0.1 volt. That's the reason why we say that roughly, approximately, surface potential is pinned to 2 times phi b. So please note that this is not exact one. You know, this guy is not exact one. So please note that we have to consider a little margin here. We have to consider a little further increase, but that is neglected in this calculation. Okay, are you with me? So if we have to introduce the real equity here, then we have to introduce this one. But anyway, this is already approximated expression. Then now we can say that, okay, source side, it is pinned to 2 times phi b, and drain side, it is increased by amount of source to drain voltage. That not that bad. So the common situation is, for example, 0 volt and 0.1 volt. In this case, we can say, okay, compared with this point, the electron it is certain that electron quasi-foreign potential is 0.1 volt higher than this point. That's true. This is given by boundary condition. But what we are currently expecting or approximating here is even our surface potential shows the same amount of increase. Why? We have assumed that now their movement or their behavior looks quite similar, okay, in this inversion case. Here we have some constraint, but before saturation. But before saturation means that we are currently neglecting the point like this. Yes. So in this case, it is completely okay to write down in this way. Oh, as I shown here, now we can introduce this kind of a simplification. So I will just skip all kinds of this expression. So now we can find simpler form. Why it is simpler? So instead of evaluating surface potential at source side and drain side, now it is readily available. Now think about the situation. Let's say your drain voltage is 0.1 volt and try to evaluate it without solving any nonlinear equation. So do you know mu effective? Yes, this is given as a certain number. W, this is the width of your transistor. This is also given. This one, L, this is the length of your channel. Yes, that is also given. Cox, once you know the thickness, equivalent thickness of your oxide layer, then Cox is given. VGS, this is your controllable quantity. Flat band, oh, this is a combination of internal quantities depending on metal work function and also substrate doping. But once you know those quantities, you can estimate this flat band voltage. And however, phi b is also function of your doping density. Yes, since you know the doping density Na, you can calculate it. And however, Vd, this is once again a controllable parameter. You control this voltage 0.1, 0.2, 0.3, so you know it. And how about all other quantities? Yes, this is universal material parameter, Q, Na, all of them are known to you. Phi b. So simply speaking, in order to evaluate this equation 3.22, you don't have to now evaluate any kind of non-linear equation. That is a big difference. So if you are a newcomer in this field, maybe you feel a little bit strange why I'm stressing this difference. But if you have any kind of non-linear equation in your evaluation procedure, then actually you have to repeat your solution procedure to get the solution. However, in this case, there is nothing required for this calculation procedure. Just you can directly evaluate it. Evaluation. So that is possible. So that is much different between nonlinear equation and just simple expression. So you can do it. So up to now, we are just considering certain case like this. In terms of gate voltage and in terms of drain voltage, usually what we draw, these are two representative graphs we must draw in usual characterization. So as a function of gate voltage under a fixed drain bias, this is a given number, then usually we draw in this way. And where are we now? Currently we are talking about the operation regime related with this point, because we are currently assuming that inversion is already occurring. So that's the reason why we say this surface potential is pinned. So this is one thing in terms of a gate voltage. And another one is we will have this kind of output characteristics. Yes, this is the output characteristics of our transistor. And when we have sufficiently low gate bias, then there will be no current conduction. So this is out of our interest currently. And where are we now? We are now talking about the entire channel can be approximated as this simple rule shown here. Oh, sorry about that. So now we can say this is the condition we are currently looking at. So in this case, we can write down quite a simple expression. Next two slides are devoted to the even further simplification of this expression. So this one is linear approximation in terms of VDS, but I think that we can just skip to the parabolic one. So in this case, we just expand our equations up to second order of VDS. Okay, so now of course this linear expression can be written in terms of as a subset of this parabolic expression. So you can find this relatively long expression. But maybe you feel, oh, this looks quite similar to one I have studied in our previous course. Maybe if you have attended the microelectronics course in your junior level or even sophomore level, then maybe you have seen it already before. It looks like this: Cox VDS minus VT. This is corresponding to the channel charge you have collected at the source side, and here you have just linear dependency. So this is corresponding to the triode mode operation of your transistor current. And here you have the second order term. So simply speaking, if I roughly draw this ID as a function of VDS, so this first term will give you just a straight line. So when we have a sufficiently low, relatively low VDS, then of course this second order term can be neglected and we will have just a straight line. However, if we go to the moderate value of VDS, then now this one and this second order term are comparable. So what we can expect is now there is decrease in its slope, and eventually it will become flattened and it will go downward once again. That is the expected behavior of this parabolic relation. Of course, you can make a good comparison between the initial one, the original one is shown here, and this is just a second order approximation of our previous equation, but it is really acceptable to expand only up to second order. Third order, of course you can do higher order expressions, but that doesn't make any help for understanding our current operation. So now you can understand there are two different terms, and quite typically, so please have a look at this square bracket part. So there is a certain number, 1 plus blah blah blah. So this looks quite complicated. So people just say that, yes, let's introduce a number, say m. So if we draw this number m, then its form becomes quite much simplified. So yes, linear term, and here we have second order term, and this is m over 2. This is the leading coefficient, and c ox VDS squared. That's it for our expression. So maybe you can ask me this question. When I attended my previous microelectronics course, actually the coefficient, the leading coefficient was just 1. So why do we have this strange number m over 2? So the answer is this introduction of m is more, as we have seen already in our derivation procedure, this is more rigorous. If we follow more rigorous derivation procedure, we have to introduce a number a number called as m. However, in our previous course, we wanted to make our life simple, and happen to be, please have a look at this one, the form of m is given as this way, and it is given as 1 plus something, and usually this something is the one we wanted to minimize. In our device engineering, people, engineers are trying to minimize this value as much as possible. So sometimes in many cases, they succeed to reduce it. So if we have successfully made technology, then usually what we can say is m is not that much higher than 1. Why? Of course, if we make a bad device, then we can generate a quite high m value. It is quite easy to destroy our device, but the one we are currently looking at is actually the engineering marvel of device engineers. So usually what we can see is the one which has quite small m values. So that's the reason why, yes, so although it is not exactly 1, so just to treat it as 1. So let me just emphasize the importance of m once again. M was really important when we are talking about planar MOSFET. Planar MOSFET has substrate, P-type substrate in the case of M MOSFET, and N-type substrate in the case of P MOSFET. And you know, in many cases, here you have the number, and if we wanted to make it 0, then how can you make it 0? of course, in order to make it 0, you can increase COx. How can you increase COx? COx is given as epsilon silicon divided by equivalent oxide thickness. So if we have extremely thin oxide, then maybe due to this quite high COx value, we can reduce this second part quite much. However, you know, the value of equivalent TOx is more and less bounded about 1 nanometer, even for extremely highly scaled devices. So this number cannot be reduced any further. And you know, here we have a certain number, NA. And if we increase NA, then of course this is counteracting to increasing this M value. So in the case of our previous planar MOSFET case, due to the existence of this substrate, anyhow our value cannot be exactly 1. It is close to 1. Then what is the, say that close? Close means 1.2, 1.3. This is the value we have seen in our previous technology called as planar MOSFET. And we are now currently talking about planar MOSFET. So this value can be just about, roughly speaking, 0.3. This is the case. So now let's come back to our previous example here. So that's the reason why if we have to write down more rigorously, then we have to teach our sophomore students or junior level students in this way. But this makes quite much complication. How can you teach them to, here we have to have a certain number. Why do we have such a kind of strange factor? Well, in order to calculate this one, we start from this long derivation. So that's the reason why we just treated it as just number 1. It was a quite acceptable approximation. And now we have this number M. Please keep in mind once again, this M should be really minimized. M close to 1 is quite important. Why? Why we have to have such kind of small M values? The reason why we have to have a minimized M value is nothing related with this current expression. This is not the main part why we have to reduce M values. So in this today's lecture, we will see why we have to minimize M to D down to 1. Okay, so anyway, let's assume that this is the expression. Then, if we just draw it, then as I told you before, so we will draw ID as a function of VDS, and first it is for low VDS, we will have just a straight line. After that, this second order term will take place, so there will be certain parabolic behavior. Then we will have the maximum value. Then where do we have the maximum value? So we have already calculated here. So if this condition is applied, how can you detect this maximum value? It is quite simple. Please calculate first derivative of your ID with respect to the VDS value. Then, you know, we have all kinds of this leading factor, but that doesn't matter, and that will give us COx VGS minus VT, and second term is just M times COx VDS. That will be the first derivative of our drain current with respect to the drain voltage, and when it vanishes means that now this curve hit its maximum value. That's the reason why we say that this condition is satisfied by this condition. COx is gone, and VGS minus VTH is divided by our factor m. M is quite close to 1. So that's the reason why we have so if I have to write down in plain English, then this one will be read as gate over drive voltage. So gate voltage referred to its threshold voltage, that is typically called as gate overdrive voltage. So gate overdrive voltage is divided by our factor m, that is the condition to have the maximum current. And beyond that, if we just follow this ID expression, then of course we will have a symmetric behavior and we will have a reduction of current. But obviously this is not physical, although we are applying even higher voltage, drain voltage, but current is reduced. This doesn't happen in our conventional MOS transistor. Why we have this contradiction? It is obvious because this equation originated from our original approximations, and we have assumed that already these two conditions, gate voltage is sufficiently high and drain voltage is sufficiently low, prevent of the operation condition like this one. This one should be avoided. However, if we apply too high drain voltage, then at the end of our drain side channel, we will have an occurrence of this bias condition. So that is just a failure of our approximation. So that is quite easy to understand. Beyond this point, our approximation is not valid any further, so we cannot apply our approximation beyond that point. So beyond that point, so well, why we have to say so, I will explain it later, but right now we just say that beyond that point the current is just flattened and saturated to this maximum value. So simply speaking, we have parabolic behavior when drain voltage is lower than gate overdrive voltage divided by m. And beyond that value, we say that this is a saturation region, and in this case we will have just a straight line. So this current level is saturation current. And as we know, when we use it as a certain transistor inside the circuit, actually the operation regime is usually this saturation regime, not in this triode or linearism. Of course, if we are talking about an analog circuit, then this part is quite important when we talk about amplifier, for example. This is critically important, but in many cases we are now talking about digital system, and in the case of a digital system, almost always we are interested with this saturation current. So increasing this saturation current is quite important. So among them, the most important one is obviously the saturation current we can observe when gate voltage and also drain voltage is maximally set to its maximum value VDD. So this is the one, and we call it as on current. When you say on current of our transistor, in many cases this bias condition is assumed. Sometimes some guys says that so say on current with a certain condition like gate voltage is VDD, but sorry, I think that the system is stuck. Okay, so VDS is almost quite small, just 0.1 volt or 0.01 volt. So this is really nonsense. That makes any sense to us. So when we are really serious about digital system, then we always have to have a well-defined bias condition for this. Both of them, both of our terminals are biased, highly biased to VDD. Okay, so this is the expression. Of course, please note that up to now, if I ask you the L, what is the actual L value? So what is your actual L value in your mind? Maybe if you are more up to date in current technology development, maybe you will say that 12 nanometer, something like that. But currently in our theory studied up to now, our formulation up to now, this level of length scale cannot be covered. In this case, please note that our theory is only valid the orders like 1 micrometer, 10 micrometer, 100 micrometer. These extremely long channel devices can be covered by this ID expression. So please note that in order to study the state-of-the-art device, we have to further develop our theory, and that will be covered in the second half of our semester. So after the midterm examination, we will talk about the non-ideal effect deviated from this extremely long channel device. So please note that L should be quite large value in our theory. Okay, so up to now we have thought about this one. Yes, so this is pinch off is related with once again saturation current. So please have a look at. And since we have just about 20 minutes left, we have to cover this very important topic: substrate current. This is particularly important if we are really interested with the digital system. You know, usually we have an analog system, analog circuit and digital one, and analog nowadays takes small part inside our entire system. Where do we use this analog part? This is it is used for interaction between external world. External world, the physical world, is analog. We are now living in, so if I say something, hello, then this sound, my voice, is recorded as an analog signal. After that is converted into digital signal. So in order to communicate this real physical world, we have to have analog circuit. However, once that information is converted into digital, then everything is done in digital. So in the case of this large digital scene, usually transistors are either turned on or turned off. On or off. That's it. The requirement is when it is on, it should be superpower. I mean that it should conduct very high current. So maximizing on current is required for this on state transistor. However, in many cases, our transistors are turned off. So now think about your cell phone. Your cell phone has billions of transistors inside it, and all over billion transistors are working at the same time. Actually, It's not. Although you have a billion transistors, but at each time instance, only a small fraction of your transistors are actually working. Then what happens to these idle transistors? Then these idle transistors, the life is just waiting. So when I bias to high gate bias, I can conduct quite a lot, but nobody calls me. I will just stay here. That is the life of our most transistors. And in that case, if they allow small current conduction, then that will directly affect our battery life. So you wanted to use your cell phone without charging, without recharging, 1 day, 2 day, weeks. That is our desire. However, in reality, even our cell phone cannot survive even 1 day. So we have to recharge it again and again. Who decided that performance? In many cases, the battery life is not determined by most powerful one because their number is so small. So many cases, the battery life is determined by the off current of idly biased transistors. That's the reason why we have to consider this sub-threshold current. Sub-threshold means that sub-threshold, your gate bias is lower than threshold voltage. That is the one. And in this case, how can we proceed? So it is not possible. For example, can we use the expression shown here? Okay. So we can use this expression. This one can be used. However, if we apply this expression, it's not, because already when our gate bias is small enough, then our surface potential cannot meet this 2 times 5e band-bending condition. Our source side surface potential cannot meet this condition, so we cannot use the equations below this part. Then we have to come back to this part. So I will just go to this substrate current part. So this is the silicon side or semiconductor side charge density, and it has 2 terms. Please note that obviously we have in reality 6 terms, but among them only 2 terms are important, and this is related with depletion charge, and this is related with inversion charge. Maybe you remember it. And in the case of this sub-threshold condition, then what we can say is this second term related with inversion charge is quite low compared with this one. This term has much higher density, density, magnitude. Then maybe you can ask me this question. Okay, then why don't you just neglect this entire term? So there is almost no inversion charge, so neglect it. If we adopted that kind of a crude approximation, it simply means that there is no inversion charge or no electron charge at all, so no current conduction at all. That's it. So in rough sense, when we turn off our transistor, that is the ideal case. Although we apply drain bias, but there is no current condition. That is really perfect case. But point is, we wanted to estimate this non-ideal off current condition. It means that we wanted to apply zero bias to our gate, but apply also high VDD value to our drain and try to measure the current. This bias condition is not intended for current conduction. Ideally, there should be no current conduction, but in reality, we have non-zero value, and amount of this non-zero value is critically important. That's the reason why we are talking about this open state or substrate current condition. Okay? Substrate means that the bias condition where gate voltage is lower than threshold voltage, and usually open current is measured at VGS equal to 0 volt. So this is a subset of or a specific case of sub-threshold regime. So that's the reason why we are talking about the entire sub-threshold regime. So simply speaking, in this bias condition, usually depletion charge dominate the inversion charge. So if we just zeroth order approximation, we can neglect any kind of electronic contribution, but that does not help our analysis. So as a next step, we must go to the first order linear approximation. If we adopt linear approximation, then now we have this kind of calculation. So please have a look at this one is corresponding to the electronic contribution to our negative charge. And actually, when we make a comparison between this and this term, what is dominant one? As we have already assumed, this is much higher in its magnitude. So this is a really small number. But point is, this first one does not contribute to ID calculation. And this second one really contribute to ID calculation. So that's the reason why, although that is quite small, but we have to keep this second term. And now we can say from this linear approximation, so inversion charge due to not exactly inversion. There is no inversion in this bias condition, because inversion means that now we have a sufficient amount of electrons. Type changes should occur. But anyway, in this case, the magnetic carrier electron can be found in terms of this surface potential and, of course, electron quasi-Fermi potential. And we have blah, blah, blah. Many terms, but they can be evaluated, and actually minus QI's, its absolute value is not that high. It is quite a small number, but it is meaningful. Okay, so then if I ask you this question, please try to answer by yourself. Then where can you find bias dependence? For example, let's say the threshold voltage is given as 0.3 volt. Yes, even in this case, we can try different cases like 0.2, 0.1, 0.0 volt. So if I change gate voltage, then of course we will have different electron densities. Then how can we have different QI values when we change gate voltage? There is no explicit dependency on gate voltage, but please have a look at here we have surface potential dependence. So if we change gate voltage, then that will change once again this surface potential. So that's the reason why we have different values for different gate voltages. So, as I shown here, surface potential is a function of gate potential. So if you change gate bias voltage, then surface potential will be changed accordingly. So in this case, surface potential is not pinned. Please note that electronic contribution is so small, so surface bending is just given as the amount of depletion charge, so it really changes accordingly. And when it is given in this form, just to insert it here, you will find quite a long expression. But here we have just exponential function on surface potential. Why do we have an exponential function? It is originated from this exponential term. Quite easy to understand. So simply speaking, ID really depends on surface potential exponentially. And so the point is, in this sub-threshold regime, ID follows phi s kBT over Q. Then our next question is, then how about the relation between surface potential, band bending, and gate bias? That is the key point. And there we have M once again. This M has, when we come back to its definition, so you can find that M is given as, what is this? Here we have a certain complicated expressions, but the physical meaning of this M is given as this form. The ratio between change of gate voltage and change of surface potential. So now think about this one. The situation is like this. Here we have a certain black box, and we wanted to make current conduction. And this current conduction is actually exponentially dependent on surface potential. And good, I wanted to change its surface potential, but let's say you don't have direct order to the surface potential. This is not your privilege. You have just order to gate voltage. So gate voltage will be changed by your will. So I will just increase it by amount of 0.1 volt, 0.2 volt. It is reflected by increase of your gate voltage. It is possible. And since there is the relation between gate voltage and surface potential, if this 0.1 volt increase is directly applied to this surface potential, then you will be quite happy. Although this is surface potential dependence, if it really follows just gate voltage and some offset value, then by changing gate voltage, you can also exponentially control drain current. But now let's think about this one. Their connection is just internally disconnected. Although we change gate voltage, let's say that surface potential tends to just stay there. I will not change arrow. Then what will happen? Although you change gate voltage, your drain current will not change at all. That two extreme different behavior is described by this M value. Let's say M has two different extreme value. One extreme is 1. Another extreme is infinitely large number. If we have infinitely large number, is that although you change your gate voltage, surface potential does not change at all. It becomes irresponsible to your order. So in this case, although you change this potential, gate potential, you cannot control the surface potential. It means that out of control. Your surface potential says that I'm not governed by this gate control. But if we consider the other extreme case, 1, it means that 1 volt change in your gate voltage is just copied 100% to your surface potential change. That is 100% efficiency for your change. So simply speaking, this low value of M means that now your surface potential is fully under control. And the value deviated from ideal value 1 means that you are losing the control over your surface potential. Okay, so that's the reason why small m value is quite important, because when we use this form, then eventually our drain current follows this exponential function, and this exponential function, just let me write down once again, ID exponentially dependence on our gate voltage, gate overdrive voltage, but here we have a certain number. This number is given as m times, this is important, m times kVt over Q. kVt over Q, this is for example 25 millivolt in our usual 300 Kelvin case, but point is, depending on our device structure, m value, we have different coefficient for this lower part. Let's say that m equal to 10 and m equal to 1. Then what will happen? Just to make a comparison, you have applied 1 volt difference to your gate voltage. Then what will happen? If we have just m equal to 1 case, then we will have change of electron current density about orders of 10 to the 40. That is corresponding to m equal to 1 case, because here we have 1 volt and m is 1 and kVt over Q is just 25 millivolt, 0.025. So we will have exponential 40. This is corresponding to almost 7 orders of 16 orders of magnitude difference in its magnitude. On the other hand, if we have a number 10, now it becomes 10 and it becomes just exponential 4. This is just about 1 order of the magnitude difference. So this is a really huge difference in our calculation. So simply speaking, changing m or having the smallest m value is so important. If we can achieve this smallest value m equal to 1, then we can make really steep dependence on our ID as a function of gate voltage. And if we have quite a high m value, then we will have this moderate dependence on our ID over gate voltage. Since we start from a certain already turned on device, then when we reduce the current, we want a steep drop of our drain current. So we want to always love to have this steep slope, and the slope is limited as the case of m equal to 1. So simply speaking, we want to have quite a small m value. Okay, I think that the time is up now. now. And since this topic is too simple, I think that I have to repeat this topic again later. So I will just cover in our midterm examination. I will just cover not in very deep way. So I will just superficially cover this substrate current part, because this is so important for actual device. So although we are talking about ID current, on current, but in reality, the most important one is, one of the most important one is actually off current. And off current and its slope and value is so important. So I wanted to stress the importance of this M value once again, and we will keep this discussion in our later lecture. Okay, thank you for your attention. See you next Monday.